As we've seen in the previous two lectures, we can generate both arithmetic and geometric progressions by either adding or multiplying by a fixed value to a previous term in order to produce the next term in our progression. In this lecture, we'll extend these ideas by studying important patterns of numbers in which the next term in our number list is found by calculating a fixed, predetermined combination of the previous terms. We'll see that both arithmetic and geometric progressions are very special examples of this much more general notion of number sequence. These more intricate number patterns are known as recurrence sequences. The most famous recurrence sequence is the list of Fibonacci numbers and their second cousins, the Lucca numbers. Now, if you're a Fibonacci fan, then you'll be delighted to know that the Fibonacci numbers will make several surprise cameo appearances throughout our course. And if you're not currently a Fibonacci fan, then I assure you that you'll be one by the end of our number theory journey. Using the Fibonacci and Lucca numbers as exemplars, we'll explore the structure and patterns hidden within recurrence sequences. As we study their growth, we'll come upon one of the most controversial and famous numbers in human history, the golden ratio. After discovering the arithmetic aesthetics of this number, we'll apply its connection with Fibonacci numbers to reveal a very clever and practical method of converting between miles and kilometers. Well, here we open by extending the ideas of arithmetic and geometric progressions. Now, for arithmetic progressions, we generate a new value by adding a given fixed number to the previous value in the progression. For a geometric progression, we generate a new value by multiplying a given fixed number by the previous value in our progression. Let's notice that both arithmetic and geometric progressions share a common trait. They are generated by the initial number, which is known as the starting seed, because everything grows from there, and then the rule that produces the next number from the previous number. We now extend this trait to produce more intricate lists of numbers. Instead of the simple rule of either adding or multiplying by a fixed number to generate the next number in our sequence of numbers, we'll now consider more interesting combinations of the previous terms to generate the next number. Just as with arithmetic and geometric progressions, the new generating rule involving the previous numbers from our sequence will remain the same as we generate the terms in our sequence of numbers. So we have this fixed rule that will follow us throughout our sequence. Now, the number lists in which the terms are found by applying a fixed rule involving the numbers that came before are called recurrence sequences. As we've seen, both arithmetic and geometric progressions, a recurrence sequence can be described precisely by just giving the first few terms, the starting seeds, and then the fixed rule that generates the next term. That's all that's required. The first starting seeds and then the rule. Everything else then is determined. Therefore, only two pieces of information are required to define a recurrence sequence: the starting seeds and the generating rule. In fact, both arithmetic and geometric progressions are each examples of recurrence sequences. In order to ground our discussion, let's consider two important illustrations. So now we're going to get our feet to the ground. The concrete examples of recurrence sequences that we're about to consider are neither arithmetic nor geometric progressions. So we're going to generate something that's genuinely new for us in terms of our work together so far in the course. Let's fix our generating rule to be that we add two consecutive numbers on our list in order to produce the next term in our sequence. So now we're going to actually require starting seeds, but now we're actually going to require two starting seeds, because the rule says that we take the two elements that are here adjacent and add them to get the next one. Then we add these two elements to get the next one, add these two elements to get the next one, and so forth. So we're still requiring starting seeds, but in this case we're going to actually need 2 in order to allow our process to genuinely get off the ground. Well, suppose that our starting seeds were simply 1 followed by a 1. So those are the first 2 elements in our progression. And now we're going to apply this rule. Well, so the process to generate the next term is to always do the same thing, which is to add the 2 previous numbers. So in our case, the recurrence sequence would be, well, 1 followed by 1. Those are our starting numbers. And then we add those 2 together to get 2. That's the next one. Then we add the 1 and the 2, add them together and get a 3. We now add the 2 and the 3 and add them together and get a 5. And if we continue, we see 8 followed by 13, 21, 34, 55, 89, 144, and so on. This famous sequence is known as the Fibonacci numbers, named after the 13th century Italian mathematician Leonardo da Pisa, who was also known as Fibonacci. These numbers appear in unexpected places, including nature and art, and they'll make several appearances throughout our course as well. Well, we can generate a different recurrence sequence by simply just changing the starting seeds, but keeping the same pattern, the same rule of adding 2 adjacent numbers to generate the next number. So now let's suppose we start with 2 and 1 as our starting seeds. Well, then the new recurrence sequence begins 2, 1, and then we add those 2 together to get 3, and then we add the 1 and the 3 and add them together to get the 4. The 3 and the 4 get added to get the 7, and the next one would be 11, and 18, 29, 47, 76, 123, 199, and so on. The list goes on. Now, this sequence is called the Lucas sequence, named after the 19th century French mathematician Édouard Lucas. Well, as we march through these sequences of numbers, especially as we walk through them as they get larger and larger, the 2 lists appear to have nothing in common. However, they do share the same generating rule, adding the 2 previous numbers to get the next one. So perhaps there's some hidden connection, some structure that genuinely connects these 2 sequences together. Well, let's see what we can find. Remember, the thing that we do in number theory is to try to explore and then uncover hidden pattern, which leads to hidden structure. Well, we know that if we sum 2 consecutive Fibonacci numbers, we get the next one on the list. What if we sum pairs of Fibonacci numbers that are 2 apart from each other? So that is to say, instead of adding these 2 to get the next one, let's add this one and this one, skipping this one, and just see what we get. So for example, if we take 1 and skip the second one and go right to the 2, if we add those 1 plus 2, we get 3. If we add the 1 and the 3, we get 4. If we take a look at the Fibonacci number 2, skip the 3 and go to the next one, which is 5, then 2 plus 5 is 7. The next pair would be 3 plus 8, which is 11. So what do we see? We see 3, 4, 7, 11. And what do we see? Incredibly, we're generating the Lucas sequence. Absolutely unbelievable. Well, let's see why this amazing phenomena actually occurs. I want us to look at an example very closely so we can actually see what's hidden behind the scenes. So let's look at the example 3 plus 8. 3 plus 8. Now, of course, we could just add it up and say 3 plus 8 is 11 and be done with it. But I'm trying to find a pattern that's going to work even when the numbers aren't 3 and 8. Well, the first thing we're going to do is use the very definition of Fibonacci numbers. So what we're going to do is we're going to write 3 as the sum of the 2 Fibonacci numbers that come right before it. So the 2 adjacent Fibonacci numbers. And then we'll take 8 and write it by its defining trait, namely the sum of the 2 previous Fibonacci numbers. So in this case, we'd see that 3 plus 8 equals 1 plus 2, that's the 3 part, plus 3 plus 5. That's the 8 part. So notice I'm using the generating rule for the Fibonacci numbers in order to rewrite the 3 and rewrite the 8 into smaller numbers. We're going to use a divide and conquer approach. We're going to try to make the numbers smaller and analyze them. So now, instead of writing 3 plus 8, we're going to have 1 plus 2 plus 3 plus 5. And now I'm going to perform a very clever trick. I'm going to take those two numbers on the inside of the sum, the 2 and the 3, and I'm going to switch the order of them. So now I'm going to write 1 plus 3 plus 2 plus 5. Now, of course, with addition, it doesn't matter what order we add, so this is still equal to the original 3 plus 8. But notice what happens when I group the first two numbers together and now the last two numbers together and add them. I no longer get the 3 plus the 8. I get something else. I now get 4 plus 7. And notice that both 4 and 7 are Luca numbers. In fact, more is true. They're actually adjacent Luca numbers. So what do we know? If we have two adjacent Luca numbers and we add them together, their sum is going to equal another Luca number, in this case 11. So that was the key idea, to write the two numbers as their individual sums and then switch these. And all of a sudden, we see two adjacent Luca numbers. When we add them up, we get a Luca number. So when we add a pair of Fibonacci numbers that are 2 apart in the sequence, we see that the sum is indeed a Luca number. Now, this example can be extended to show that the result holds in general. And a rigorous proof involves a technique known as mathematical induction, which is basically, in some sense, this divide and conquer approach. The method involves using the smaller cases to show the validity of the result for the larger cases, just as our example really illustrated. As in the previous lectures, with the progressions that we studied earlier, we can consider the sum of the first few terms of the Fibonacci or Luca sequences. So let's consider them right now. If we compute the cumulative sums of the first terms of the Fibonacci sequence, what would we see? Well, we'd see 1, that's just the first term, then 1 plus 1, 1 plus 1 plus 2, 1 plus 1 plus 2 plus 3, 1 plus 1 plus 2 plus 3 plus 5, and so on. And what are those sums? Those sums equal 1, 2, 4, 7, 12, 20, 33, and so on. Well, what do we see when we look at these numbers? The answer is not much. Okay, that's okay. It means that maybe something more subtle is going on. What if we take this list of numbers that we just found, this sum, and what if we add 1, the number 1, to each number on our list? So I'm going to increase every number on this sum list by 1. Then what do we see? We see 2, 3, 5, 8, 13, 21, 34, and like magic, we return to the Fibonacci sequence. Absolutely amazing. Well, can this magic be explained by mathematics? Well, the answer is yes, and we actually are going to use what I think of as a domino idea. We're going to consider the sum of all the Fibonacci numbers up to a certain point, and then what I'm going to do is I'm going to add that extra 1 that we're supposed to add at the very, very beginning. At the very, very beginning. And let's see what happens. What's going to happen, by the way, is that 1 at the very beginning is going to create a chain reaction. And all of a sudden, the sums are going to implode into Fibonacci numbers, and we're going to get this entire collapsing down to just 1 Fibonacci number, as we've seen in the illustration of the examples we looked at. So let's actually consider an example. Let's take take 1 plus 1 plus 2 plus 3 plus 5. That's the sum of the first few Fibonacci numbers. And then we're going to stick on a 1 at the very, very front of that. Now, what do we see? Let's just add the first two numbers together. That's the new 1 plus the first 1 that we had in the Fibonacci list. And what do we see? 1 plus 1 is 2. And notice that 2 is, in fact, a Fibonacci number. What's the next number in our sum now? Well, it's a 1. And notice that 2 and 1 are adjacent Fibonacci numbers. So their sum, which is 3, yields another Fibonacci number. So now we have 3 plus 2 plus 3 plus 5. Well, 3 plus 2, those are 2 adjacent Fibonacci numbers. So when we add them together, we get the next Fibonacci number, which in this case is 5. So now our sum has collapsed down to 5 plus 3 plus 5. And notice that 5 plus 3, well, that generates the next Fibonacci number because 5 and 3 are adjacent Fibonacci numbers. So I see 8. So I have 8 plus 5. 8 plus 5, we have, again, adjacent Fibonacci numbers, so the sum is 13. And this is the idea, and a similar result actually holds for the Luca sequence as well, which you're free to think about if you want. But the point here is that when we collapse this down, we see 2 adjacent Fibonacci numbers. However, in this instance, the adjacent Fibonacci numbers are kind of reversed in order. It's first bigger plus smaller, but still adjacent, so the sum is a Fibonacci number. Well, We now return to the growth of recurrence sequences of numbers. So how are these numbers actually growing? Well, since the term we add to one Fibonacci number to generate the next one is ever increasing, we're not adding a fixed amount, we're always adding a number that comes right before the previous Fibonacci number in order to generate the next one. We know that the Fibonacci sequence is not an arithmetic progression. But perhaps the Fibonacci sequence is a geometric progression. That's possible. So remember that a geometric progression is one in which the ratio of consecutive terms in the list is always the same. So let's look at the first few ratios and see if it's constant. 1 divided by 1, the ratio of the first two terms equals 1. The ratio of the next two terms, 2 divided by 1 is 2. So that's not 1, so we're already done. Let's just take one more example. 3 divided by 2 is 1.5. And so clearly these ratios are not equal, so we see that the Fibonacci numbers do not form a geometric progression. But these numbers are near each other. We got 1, 2, 1.5. They're all kind of hanging around the same area. So maybe there's something else going on within these ratios that requires actually a closer look. Well, this time we're going to write the ratios in a different way, one that actually captures the generating rule for producing the Fibonacci numbers. So let's look at the ratios again. Well, we have 1 over 1, which I'm just going to keep as 1 over 1. I'm not going to simplify it to just the number 1. Now, the next ratio is 2 over 1. And how did we get the 2? We got the 2 by adding 1 plus 1. So let's now write the 2 as 1 plus 1 divided by 1. Which, notice the first 1 over 1 is just the number 1. There's a lot of 1s here, by the way. Plus 1 over 1. So 2 actually can be written as 1 plus 1 over 1. Probably the most complicated way of writing 2 you've ever seen ever. But I want us to write this way because I'm searching for a pattern. Now let's consider the next ratio, 3 over 2. Well, again, I'm going to apply my rule of writing how 3 was born. 3 was born by taking 2 and adding 1 to it. So we see that 3 equals 2 plus 1. We're dividing that all by 2. So we see 2 over 2 plus 1/2. Well, 2 over 2 is just the number 1, so we have 1 plus 1/2. And notice that 1/2 is the reciprocal of 2, which was our previous ratio. So if I take the reciprocal of the previous ratio, that's equal to 1/2. And so I see that 3/2 is 1 plus 1 over 1 plus 1 over 1. Interesting. Lots of 1 plus 1 over 1s. Let's look at 5/3 now. Well, 5/3, I'm going to just follow the same process. I'm going to write 5 by its defining trait within the Fibonacci list as 3 plus 2. And then when I break up 3 plus 2 all divided by 3 into two fractions, I see 3 over 3 plus 2 over 3. Well, 3 over 3 is just 1, so I see 1 plus 2/3. But notice again that 2/3 is the reciprocal of the previous answer we found, 3/2. So therefore, I could take the previous answer and just take its reciprocal to get that second term. And so I see that 5/3 equals 1 plus 1 over 1 plus 1 over 1 plus 1 over 1. Amazing. So even though these ratios are not constant, they do have a predictable and even fascinating form. They're an ever-deepening expansion of fractions of the form 1 plus 1 over 1 plus 1 over 1 plus 1 over, and so forth. If we now imagine continuing this pattern endlessly, then we arrive at an endless fraction within fraction of the form 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over forever. Now, as improbable as it may seem, this expansion has a numerical value, and it's actually a very special number. This number is called the golden ratio. Well, this representation of the golden ratio as an endless fraction within fraction is actually an example of what we call a continued fraction, which we'll study in some depth at the very end of this course. We now wonder if the golden ratio can be expressed as a more familiar-looking number. We notice that if we call the golden ratio by its normal name, which we use the Greek letter phi, then we have that phi equals, and I want us to visualize this, phi equals 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over endlessly. That's the definition of phi. Whenever we see an endless list of 1 plus 1 over 1 plus 1 over 1 plus 1 over endlessly, we know that that actually equals phi. Now I'm going to perform a little magic trick. Let's take that expression and just cover up the first 1 plus 1 over. What's left right here? Well, it's actually an endless list of 1 plus 1 over, 1 plus 1 over, 1 plus 1 over, and so forth forever. So that piece right here is actually another copy of the golden ratio. It's another copy of phi. And so what do I see? I see that phi equals 1 plus 1 over phi. Phi equals 1 plus 1 over itself. It's almost a peculiar identity that we're finding, because we're seeing that phi actually is inside of itself in some crazy way. The important thing for us is that this actually can be viewed as an equation, and now we can actually solve for this number phi. Now, if we do that, I'll first multiply both sides by phi, because no one likes having an unknown in the denominator. So I'd see phi squared equals phi plus 1, because phi over phi would just be 1. And now I see phi squared. That means it's a quadratic, which if you remember from your old school days, the way to solve a quadratic is to have everybody go to one side. It's a big party at my house. Come on over, and we have to have the thing equal to 0. So then I'd see phi squared minus phi minus 1. If I subtract the left-hand side over, then the left-hand side over, then we'd see simply phi squared minus phi minus 1 equals 0. Now, using the quadratic formula, which we saw in grade school, we can actually find the two solutions to this. Now, there will be two solutions because it's a quadratic. That exponent is a 2, which means we'll have two answers. One solution is 1 plus the square root of 5, all divided by 2. And the other solution is 1 minus the square root of 5, all divided by 2. Now, that second number, 1 minus the square root of 5 all divided by 2, is actually a negative number. And since our number phi starts off with 1 plus and some positive number, we know it's going to be a positive answer. And so therefore, we use the other solution. And we just discovered that phi, the golden ratio, equals 1 plus the square root of 5 all divided by 2. Now, the decimal expansion for phi, if you now plug this into a calculator, 1 plus square root of 5 all divided by 2, we'd see that phi equals 1.618033989, and it goes on and so forth. Which, by the way, when viewed as a decimal number, just seems like almost like a jumbled random screed of digits, and we completely see hidden from sight the structure of phi that we've already uncovered. So a great life lesson, again, which we've seen time and time again, that when we look at things in different light, all of a sudden we might see structure, whereas another view might hide it. Well, we now see that the ratio of any consecutive Fibonacci numbers is approximately equal to this number phi, 1.618033, and so forth. And the larger the Fibonacci numbers get, the closer the approximation is, in fact, to this golden ratio. Well, while phi is one of the most famous numbers, it is also one of the most controversial. Many believe that the golden ratio informs our aesthetic tastes, appearing in nature and art, while others strongly disagree. And in fact, this is quite a big bone of contention amongst many people, fans of numerology, fans of number theory, and fans of the arts. For example, a famous example that people sometimes point to is the Parthenon and in the Acropolis, and whether in fact within the Parthenon, if we look at the dimensions and look at the rectangle formed by circumscribing a rectangle around the Parthenon, if in fact, if you look at the base ratio of the base length to the height, that ratio would be the golden ratio. Rectangles that have this property, rectangles that have the property that the ratio between the length of the base to the length of the height is exactly the golden ratio, are referred to as golden rectangles. And so the question is, do we see a golden rectangle within the Parthenon? And the answer is probably no, because of course this number is infinitely complicated. The decimal expansion goes on forever, so it's hard to measure exactly. But are we drawn to that particular type of shape? Are we drawn to the aesthetics of this number? Many people believe no. Many people believe yes. And so it remains a wonderful debate. In fact, the golden ratio does appear in many different areas of number theory and science, and that remains a fact. The number is important in our work in mathematics and science. It's also a fact that the golden ratio is the only number that can be expressed as such an endless continued fraction consisting solely of ones, in the fashion 1 plus 1 over, 1 plus 1 over, 1 plus 1 over forever. So, by the way, we'll return to the golden ratio later in this course and see that it actually has a very important role to play in our study of irrational numbers. Certainly within the world of number theory, it would be difficult to argue that phi, the golden ratio, is not an abstract object of great importance and beauty. So while we can debate whether it appears in nature and in aesthetics, it certainly appears in mathematics, and it certainly, within that realm, is an aesthetically appealing and important number. Well, I want to close this lecture with a practical application of the Fibonacci numbers and their connection with the golden ratio. So here's an actual thing we can use in our everyday lives. Recall that we found the value of the golden ratio to be around 1.618, which coincidentally is extremely close to the number of kilometers that equals a mile. In fact, 1 mile equals 1.6093 something kilometers, which is really close to 1.61 something. Well, we can actually use the Fibonacci numbers to convert between kilometers and miles. And let me illustrate this with an example. So for example, 13 kilometers is approximately 8 miles, since 13 over 8 is approximately 1.6. Now, how did I get that? Well, since 13 is a Fibonacci number, all I did was find the Fibonacci number that comes right before it, which is 8. And we know that that ratio, 13 to 8, is going to be very close to the golden ratio, which is very close to the conversion ratio for kilometers to miles. And so what I see here is that 13 kilometers is approximately 8 miles. So if you have a Fibonacci number of kilometers to convert it to miles, just look at the Fibonacci number that comes right before. Well, to illustrate the method in general, let's now try to approximate the number of miles in a 10-kilometer run. Well, first we express 10 as a sum of Fibonacci numbers. In this case, notice that 10 equals 2 plus 8. Next, we just follow the procedure we just saw. We replace each Fibonacci number in our sum with the Fibonacci number that precedes it in the Fibonacci sequence. In this case, we replace the 2 by a 1 and the 8 by a 5. And so instead of 2 plus 8, we now consider 1 plus 5. And if we add 1 and 5, we get 6. Therefore, 10 kilometers is approximately 6 miles. And if you've ever run in a 10-kilometer race, you know that's right, because in fact a 10-kilometer race is about 6.2 miles. So really a close estimate just using the Fibonacci numbers. How long is a 10-kilometer trip in miles? I'm sorry, let's do a 50-kilometer trip. So how long is a 50-kilometer trip in miles? We first write 50 as the sum of Fibonacci numbers, which, by the way, you can always do by taking a look at 50 and backing up until you see the very first Fibonacci number that you come to, which in this case would be 34. And then you'd be left with 16, and so you keep backing up until you hit the next Fibonacci number, which would be 13, and then you back up more until you get to 3. So 50 equals 34 plus 13 plus 3. And now if we take each Fibonacci number and replace it by the Fibonacci number that comes right before, we would compute 21, replacing the 34. The 13 would get replaced by 8, and the 3 would get replaced by a 2. And so we now see our sum would be 21 plus 8 plus 2, which is 31 miles. Now, in actuality, the mileage conversion of a 50-kilometer trip is actually 31.06 miles. So incredibly close to 31. You could see how wonderful this approximation really is. Well, practicality aside, we've now seen the world of recurrence sequences, which takes the foundational ideas we saw with arithmetic progressions and geometric progressions and extends it to a wide range of important number lists that include the Fibonacci and Lucca numbers.